You guys got so quiet. All because I start recording, you get quiet? Or is it because I'm about to teach you that? Oh, it's that. That's how it's supposed to work. It is. So we started this yesterday. Some of my other classes, I decided after going through with you guys that I would just completely hold off on showing page 10 until today. So for some people today, this might be new. Those of you who have been in Mr. Mita's lab the past 2 days, though, you've been doing this. Did Mr. Winter start this? Okay, he's probably starting either today or tomorrow too. So here's where we left off yesterday. I was showing you this apple and describing how it was similar to the earth. And it's kind of even accurate to represent how thick and thin different layers are. So I did add in this drawing that shows, okay, I took the whole apple. I cut the apple in half so you can see the inside. And then I just want to focus in on this quarter of the apple. If I was to erase the rest of this apple that's on the outside and only focus in on this like pizza slice of it, you could still get the idea that if you were up here, this is the outside of the apple and it's working towards the inside. And I like to show that because it is similar to this part of the reference table that they give you here. So on this reference table, just like the apple, this is the outside of the earth, and we work our way towards the earth center. And the earth center is labeled pointing right here at that 90-degree angle in the center of what used to be the apple. Now it's the center of the earth. So I started yesterday describing that this reference table is broken up into 3 main sections. We have a drawing of what the earth looks like, and then we have 2 graphs below it. So we'll start off with these graphs. Both share the same x-axis. They both show depth. The bottom graph is a depth and temperature graph. And then the top graph is a depth and pressure graph. One thing I want to point out about the pressure graph is that this is in millions of atmospheres. So atmospheres is a way of measuring pressure on the earth. Right now, where you guys are sitting, you have approximately a pressure of 1 atmosphere. Any idea where they get that unit of measurement, 1 atmosphere? It is the air pressure on the surface of the earth, but what I'm asking is, where does that number come from, 1 atmosphere? Yeah, but why 1? Yeah, because there's only 1 actual atmosphere on us right now. So you might not realize this, but the air in the atmosphere actually has some weight pushing down on it. Without the atmosphere, you would not, life would be different. So that weight, it's not gravity, so don't get gravity and pressure switch. But the atmosphere does have weight. Do you guys feel it in your hand right now? You don't. You don't feel it in your hand. What if I told you that the weight of the atmosphere is 14.7 pounds per square inch right now in your hand? That means every square inch of your body has 14.7 pounds of pressure pushing down on it just from the air above you. Around. Sometimes it's less, sometimes it's more, depending on the weather, but it's always around 14.7. So you feel it? You guys must be pretty strong. You got there's a lot of square inches on us. You buck? You don't feel it. Yeah, you don't feel it because it's been something that you've experienced your entire life. If we magically took it away, you guys know when they take away pressure? No. You guys ever watch those TikTok videos about things in a vacuum? Few of you that know what I'm talking about. Okay, here's your homework. You have to watch 1 TikTok or YouTube video about an object in a vacuum. Okay, we might have time at the end of class to watch a couple. Yeah. Okay, I'll show you one in class. So it doesn't have to be a TikTok, but you can just go on YouTube and say objects in a vacuum, and you'll see what happens when pressure gets removed from objects. It's a lot like, okay, have you seen any of those videos of mattresses that are shipped to people. Okay, these come up. I've seen them even on Ridiculousness. You guys watch Ridiculousness?
Yeah.
Yeah, it's a good one, right? It's funny. Okay, it's a lot like just sitting there watching TikTok, but anyway, when you remove the pressure from stuff, it expands. So you would notice a difference if we did not have pressure on us right now. But anyway, so we have a pressure of 1 atmosphere on us. Again, that number comes from the fact that we literally have 1 atmosphere above our head. So there is 1 atmosphere of pushing down on us. So this is in millions of atmospheres. So it does start down here at 0, which is pretty much us. But you go up and it's 1, not 1 atmosphere, but 1 million atmospheres. So it's a lot more pressure than we're experiencing here. Yeah, this times a million is here. This is us times 4 times a million. So that's a lot of pressure there. But anyway, we'll talk about that as we go along. So these are just regular graphs. And I'm sure you can read these regular graphs. What if I asked you, what is the temperature at a depth of 4,000 kilometers? So I'm actually asking you that. So all of you do it, don't shout out your answer. So my question was, off of this reference table, at a depth of 4,000 kilometers, what's the temperature? So actually read your reference table. Depth of 4,000, what's the temperature? Somebody walk me through how to do it. Don't tell me the answer. What do you do if you have a depth of 4,000 and I ask you what the temperature is? Where do I start? Yes, we go to a depth of 4,000. Then what? Go up till you hit the dark line that's labeled temperature. And then you go over. So it does require a little bit of estimating. We go over. And what would you guys estimate that to be? So we went to 4,000 up till we hit the line, go over. What would you estimate that to be right there? It's 5,000 what? Okay, did everybody say something like that? I heard a bunch of people all at once. So around 5,800. Did anybody think it was 5,500? Why not? It's right. That is a little bit higher than halfway. So that's the kind of estimating that you would have to do. If you said 5,600 or 5,700 or 800, probably even 900, they'd give you credit. So it doesn't have to be dead smack on as long as you saw that it was higher than 5,500. So you guys know how to read a graph, right? How about if I went the other way? How deep would you have to go down to find a temperature of 5,000 degrees? So I want to know at what depth is the temperature 5,000 degrees? So everybody try this out on your reference table. So again, at what depth would you find a temperature of, oh shoot, what did I say? 5,000, okay, thank you. At what depth will you find a temperature of 5,000? Again, can somebody walk me through how to do that? Don't just shout out the answer. TJ, how would you do this? On temperature this time, we go to 5,000. So we go to 5,000, then what? Go right until I hit the black line, which happens to, it looks like right here, right? And what'd you guys estimate that to be? Yeah, it looked like it was right on the 3,000 for me. So this is not baffling, right? It's just a graph. Could we do the same thing with pressure? So how about this? What is the pressure? What is the approximate pressure at a depth of 5,000? At a depth of 5,000, what's the approximate pressure? Pressure. Okay, so I go to 5,000 depth. Go up, but I don't care about this number because this is temperature. Go up, I want to see the pressure. So the pressure is 3 what? 3 million atmospheres. So you guys know how to read the graph parts. They then tie the graph into the picture. And here's where we're going to start to color. I'd like you to grab any color that you wish. And we're gonna start with, I think I'm gonna start from the inside and work my way out. So I would like you to go ahead and pick whatever color you want. By the way, if you want to save your biggest or the most coloring for your favorite color, this is not it. So don't pick your favorite color if you want that to be your biggest color. So you grab your, I'm going with green. I'm going to color my inner core green. By the way, don't color so darkly that you can't see underneath it. We do need to see the words that are under there. So this is the inner core. Did you notice that you colored anything like important? It says iron and nickel. Why do you think it says there's iron and nickel there? That's what's in it. So the, where am I trying to go with this? The inner core is made out of iron and nickel. Then we're going to come over here and color this 12.8 to 13.1. Can you figure out from this graph what those numbers are? That's the density. So see here how at the top of this reference table, density is listed here. So the Earth's core has an inner core has a density of 12.8 to 13.1. What do you think about those numbers? Too low? What's the density of water? 1. Do you remember the density of galena? Anybody remember that? In case you forgot, we could look 7.6. So if any of you have picked up McKenna's sample of galena here, any of you have noticed how heavy this rock is? Who's picked it up besides McKenna? Pretty heavy, right? This has a density of 7.6. The inner core is almost, a little short, but almost twice as dense as that. So we're talking about some really, really dense materials. So that's the density of the inner core. Now, do you see how this dotted line follows down? That is marking off the inner core so we can see where the inner core's temperature, pressure, and depth are. So go ahead and color that all the way down. Don't go over the dotted line. Hopefully you noticed, what did you notice about the pressure of the inner core as you were coloring over it? How much pressure does the inner core experience? A lot. That's what I really was hoping you'd say. It's got a lot. Now, it depends on exactly where we look. At the top of the inner core, meaning like if not the deepest section of the inner core. So right here, the inner core is about, what do you say, maybe 3.1, and up here maybe 3.6. 3.6 million times as much pressure as we experience here. So when we say a lot, we mean a lot of pressure at this Earth center. Not quite as much at the top of the inner core, but still way more than we can handle. Same with temperature. How hot is it in the inner core? Very hot. Down here, 6,200 to about 6,600 degrees Fahrenheit. Keep in mind, water boils at 100. I lied, this isn't Fahrenheit, it's Celsius, sorry. But water boils at 100, and we're talking about 6,200 to 6,600. How deep is the inner core? Very. How deep? Can we figure that out from here? How deep is the inner core? Over 5,000. What if they asked for a range? So over 6,000 is how deep it gets, but what if we ask for a range? So is it at 5,000, I guess is what I want to ask. Not really. If you say 5,000, I have to mark it wrong. So notice that the dotted line is a little past the 5,000. So it is perfectly clear that it is not exactly 5,000. So if they don't say approximately, I do need you to read it off the reference table. Yeah.
On the outside of the core goes from 11,192 degrees Fahrenheit.
Hang on, let me write this down because somebody will ask me later. So 11,000. Okay.
11,009.
Okay, so the inner core in Fahrenheit would be 11,912 degrees. That's pretty hot.
We can also, if you want to talk about, we can just round up and say 12.
You're right. But really hot is what we're getting at. Going back to the depths though, make sure you realize that it's not quite at 5,000. And how deep does it go? What is that number you're thinking over there? Very. Is it 6,000? It's over. Is it 6,500? Why do you say no? I agree. This does not look like a whole half of a box. This is a little short. Guys over there, stop talking. Couple more things. Is the inner core solid, liquid, or gas? And how can you tell from this reference table? Everybody think about that for a minute. We did take notes on it yesterday. But how can you tell from this graph? Nope, it's not the way they represented in the drawing. Do you see it, Cam? Notice that melting point and interior temperature are labeled. Did you also see that? Nice job. So if you notice, the interior temperature is colder than the melting point. Think that through. Today, it's colder than the melting point of water outside. Right now, it is 26 degrees Fahrenheit outside. It's colder than 32, the melting point of water. So what's happening outside? Instead of raining. We have solid water falling from the sky instead of liquid water because it's colder than the melting point. It's too cold for the water to melt. Same deal here. The actual temperature is too cold to melt, so it's still a solid. So they tell you a lot of the things you just got to know on this reference table. Let's keep going and do the inner core. So pick another color, probably your second favorite color. We're going to do the same thing at the top. We're going to color the outer core. Noticing again, it's made out of iron and nickel. Going over to the density, you'll see it's a little bit less than the density of the outer or the inner core. Follow that sucker down again. Being careful to stay inside the dotted lines for the outer core. So you should be able to read the temperature, the pressure, and the depth for the outer core. Again, make sure you're not coloring too dark that you can't see underneath your coloring. You did a good job coloring? No.
I did not say that.
Oh, good thing we're past grading on coloring. Hey, by the way, is this layer solid or liquid? Is the outer core solid or liquid? The outer core? How do you know from this reference table? So again, we take a look at the actual temperature and the melting point. Now, the actual temperature is actually higher than the melting point. So in this case, it's not like today, and it wouldn't be snowing, it would be raining. It's hotter than the melting point. So that means the rock has melted, and this is a liquid layer. All right, we're gonna do the next layer for coloring, and I need you guys to pay attention for this one. So we're gonna color the mantle. Like the good old days when we only called it one layer of the mantle. But there's really 3 different sections of the mantle. So to do this, what I need you to do is notice the densities. Do you see how the polka dots, the gray, and the white layer all are in this 3.4 to 5.6 range? But they're clearly different layers. So I want you to follow this, that where the solid gray and the polka dot layer come over, give yourself a line there and color down. That's the stiffer mantle. But we're going to then include the asthenosphere in that section as well. So you're going to bring your orange over, or whatever color you pick, sorry. And then there is one more very small layer. What is this very small layer called right here? This is not the crust. This is not the lithosphere. This section is, no, the asthenosphere we already did. That little section is the rigid mantle, still part of the mantle. It is part of the lithosphere, but it is also the mantle. Good morning. Yep. Yep. Bye. Sam, when the bell rings, we need you in guidance. So now you should be getting close to having everything colored up here. Give you a little bit longer to color. I will also direct you to your homework. Your homework will be to start using this reference table, which is page 3 of the packet you picked up yesterday. Your homework is page 3 from the packet you picked up yesterday. If you weren't here yesterday, make sure you grab a packet. Oh, weirdly that one. So page 3 is just getting used to using this reference table. So I'm just asking you some questions such as what 2 layers make up the lithosphere? By the way, you can do this one off the top of your head, or it is right on that reference table. Where do we find it on here? Right there. Yep. Right here is where it says lithosphere, and it puts in brackets that it's made out of the crust and rigid mantle. So every single one of these, the answer can be found right in your reference table. 3. Guys, can I also ask you a question? I think we talked about this yesterday. Are you guys aware what the word rigid means? We did talk about it. Let me just make it clear, because I think this is a huge misunderstanding. And I actually know for a fact that my 7th grader had this as a vocab word for her ELA class. She also didn't know what it meant. So rigid does not mean it has ridges. Even if it makes it look like a saw blade, that would be rigid, it has ridges on it. That's not what rigid means. Rigid means it doesn't move, it's unbending, so basically a solid. Mrs. Ritz?